Hey, welcome back. This is Mr. Wakefield, and we are starting Chapter 3 and our new worksheet packet as a result. Um, you see here in Section 3.1, we have, it says graphing quadratic equations. All right. Here's the two different forms that they're going to come in. All right. And we've graphed stuff before, right? In Chapter 2, we graphed lines, didn't we? Okay, we graphed some other things too, like circles and stuff. But what is the difference there? How are we going to be able to tell the difference? Let me show you some examples of that here. Okay. Here we go. So if you had, for example, and this is a little bit different because we have we went off the graph and found the equation, but it's still the same idea where if you graph something like this, okay, it's going to be a line. What is different about this compared to what we're about ready to do? Well, this right here back in chapter 2 was in this form right here, okay, where you had f of x equal to the mx plus b form. When it's like that, you know, like negative 2x plus 1, or like this one over here, 3 halves x minus 2, where it's just the x term to the first power, x to the first, and then no x at all. That's when it's going to be a line. Conversely, if you've got f of x equal to something that has x squared and then x and then the constant, all right, that's going to be a whole different kind of graph, and mainly because of the x squared. All right, we'll take a look at what that is. But you can see the difference there between just the mx plus b form and when you have the x squared in there instead. Another thing that you'll see is one that looks like this, where you have two terms in here. You have just x to the first power, but because that bracket's being squared, it's similar to when you have x to the second power. In fact, if you were to distribute out these brackets and get rid of them by squaring the bracket, don't do that, okay? You don't have to do that. But if you were to, then it would be equivalent to this. And so that's the reason why these two things should have the same graph then. It's because theoretically they are equivalent to each other. So what is this thing that the graph looks like when it looks like one of these two forms? It's going to be not a line but a parabola. Parabola is what? Parabola is one of two things, you guys. I got it written down over here on a separate sheet here. It's either going to look like this right here, going straight up like that, or it's going to go straight down like this. In fact, we saw that earlier with variations of the x squared function back in 2.7. We saw those, all right? And so this is also kind of basically revisiting that a little bit. But it just, one thing we didn't see in 2.7 was this one right here. All right, this one right here, we didn't see something like that. In fact, I'm going to talk about that right now. It says here, when it looks like this, you can use the 2.7. I'll talk about why in a minute here. Whereas when it's like this, you can't. So let's talk about that, just in case you're interested in doing the 2.7 method, but you don't have to in either case. But you could in the first one if you really wanted to. So let's talk about that for just a moment here, and then we'll get into graphing these things here in section 3.1. Back in section 2.6, what we were doing was we were building off of these 5 basic graphs right here. Okay, for example, if you saw a problem like this, which is actually the first problem in the section 3.1 right now. Okay, if you saw a problem like this, we would have been able to graph it back in section 2.7 using, remember in 2.7 we had those problems where we would set the 5 different things equal to the original 5x values. You get the new x's, you get the new y's. Go ahead and look back at your worksheet packet to review that if necessary. But that's what we were doing, is we were building off of any one of these 5 graphs. And since you have this thing right here being squared, all right, we built off of the x squared graph. So if you have something being squared that is not just anything, but it is something that is a polynomial inside this bracket that has just x in it, not x squared or x to the third, but just x in it. If you've got something like that being squared, okay, and then you multiply that result by a constant number, not a variable out here, but a constant number, and then you add all of that to something else in the back here, or this could also be subtraction, that's okay. When all those things happen, the thing on the inside being squared with x to the first power being multiplied by a constant, and then added or subtracted with a constant back here, that's when you can use the 2.7 method to build off of the x squared to graph that. So you can actually do that on the very first problem here in section 3.1. I'm going to show you a different way, but just to give you that option. Now, the second problem in section 3.1 looks like this, and let me tell you why you cannot use the 2.7 method, but rather you need to use the method I'm about to show you here in 3.1. The reason why is because in order to be able to use the 2.7 method, you need to be able to take either something squared. It doesn't have to be x, but it could be x. So see how here the x is being squared here? Okay, that's okay. It doesn't have to be x minus 2 squared. It could be just x squared. But the problem is that what did we say had to be true after we established that something with the variable in it was being squared? We had to multiply by a constant and then add a constant or subtract a constant after that. All right, well, the problem with this is that after you establish that we have x squared here, okay, the x is being squared here, we then multiply by a constant. That's okay. All right, that's being multiplied by a constant too there. But then are we adding or subtracting a constant behind that like we were with the plus 1? No, we're not. Okay, we have the x there being subtracted. And so because of that, you cannot use the 2.7 method. So as I mentioned in 2.7, that method in that section does not apply to every single graph. It applies to a lot of them, but not all of them. So you could do it with this. You can't do it with that. But in section 3.1, I will show you a different method for both of these. Okay, so you know all your options. Let's go back to 3.1 right now and talk about that. What is that method that we're going to do here in section 3.1? It says here that when you have something that looks like this, which is just like problem number 1, all right, it's a parabola with vertex HK. Okay, well, let's stop right there. First of all, you guys, the constant numbers in this thing are the A, the H, and the K. All three of those letters are constants. We just don't know what they are yet, so they look like variables, but they're actually constants. All right, what do they mean? Well, the H and the K form the vertex. The vertex, remember, is that thing that is either at the bottom of the parabola. All right, so here it would be 0, 0. Or if the parabola goes up and if it goes upside down, all right, then it would be this thing up here at the top. All right, that's what the vertex is. It's either this thing here or it's this thing here if it goes up. All right, and what it does is it cuts the parabola in half and both sides look the same. We talked about that before in section 2.7. It's no exception here. All right, so that's what the vertex is. What would the vertex be then here in this first problem? It would be, and we got to be very careful about this. Notice the formula says, we kind of talked about stuff like this back when we were talking about circles. Because this says minus right here, I'm actually going to change the sign of the number that's in here with the x in order to figure out the h part of the vertex. So since this says x minus 2, the h is actually going to be just 2. All right. Again, we saw that similar thing back in section 2.2 when we were talking about circles. All right. We saw x minus h in there as well. We do the same thing. What's different, though, compared to circles is that here it says plus k, not minus k. So because it's plus k, then that means you do not change the sign on this. So if it says plus 1, then the k part is just going to stay as 1. If that had said minus 1, for example, then this would become minus 1. All right. Now, please don't go ahead and graph that just yet, because we don't know if we need to change the scale, like if the numbers get real big or something like that. So don't do that just yet. Notice in the directions here it says give the vertex. We did that. The axis is that dotted line, you guys remember, that goes through the vertex like that. that cuts the graph in half. So we'll put that on there as well. It also mentions domain range and the intervals on which the function is increasing or decreasing. Don't worry about that yet, okay? We'll get to that in just a few minutes. The main thing, though, I want you to also know is that we also need to include what? We also need to include at least 1 point on each side of the axis of symmetry. Okay, back in 2.7 we had a total of 5 points. You don't need to do that here if you don't want to. You just need to have the vertex and then 2 additional points, but it's got to be at least 1 on each side of the vertex. So I want to make sure you understand that that is also expected just as a part of graphing a parabola. And we now know that a quadratic function is a parabola. So since they're telling us to graph the quadratic function, we know that that's the expectation. All right, now, so make a note of that, though. So now we want to find out 1 point on each side of the vertex. So the vertex is at x equal to 2, right? What I mean by finding a point on each side of the vertex is like this. Since the vertex is at x equal to 2, you just need to pick an x value on each side of that. All right, so if it's a 2, then 1 and 3 are good choices right there. All right. If, for example, the vertex had been at 4, then you'd choose, say, 3 and 5. Okay, 1 on each side. That'll be fine. What's cool about this, though, is that both of these numbers are going to give you the same answer. So you only need to plug in one of them, and then the other one will automatically be the correct thing, the same answer. So let's plug in, say, 1 right here. Okay, if I plug in 1, I get this right here. Again, I'm going to do order of operations like I always do when I plug into f of x and figure out what the answer is. That would give me this right here, parentheses first, and then exponents, okay, multiplication, and then addition, and I get -2. Because of how a parabola works, you guys, whatever number, as long as it's the same distance away from 2, like let's say that this was 2 right here, okay, 1 and 3 are going to be the same distance away from 2, aren't they? Can you see there that the y values should be the same? If they're the same, if both points are such that one of them is not higher or lower than the other, see how they're like along the same level here? You don't have 1 point. I'm pointing at these 2 points right here, okay? Not the vertex, but these 2 points. All right, if these 2 points are on the same level and one is not higher than another, then that means they have the same y value. And that's how parabolas work. If you pick 2 numbers that are the same distance away from the vertex x value, which is 2. All right, 1 and 3 are the same distance away from 2, and so we can automatically assume, you guys, without having to do any additional work, that if 1 gives me -2 for y value, then 3 also should. And so I apologize if I fell off the page there, by the way. That ended up being -2 right here. Now you can see that. Let's make a note of that right there. And so I now have enough information to graph this. And since these numbers are fairly small, I don't need to like adjust the scale of the x and y axis like I have in some problems in the past. Here are these points right here, right there, and right there. And so now, as you guys know, as we talked about back in 2.7, a parabola should be what? It should be smooth. Okay, it should look the same on both sides of the axis of symmetry, as we call it, axis for short. Okay, that's this dotted line that goes down here. All right, and it should have arrows on both sides. So let's do that. Let's make it smooth, not a pointy edge. Make sure this is like a U shape upside down and not a V shape upside down. All right, make sure it looks the same on both sides. All right, it wants you to put this axis in here. This axis needs to be a dotted line, you guys, not a solid line. Solid line would make it look like the points on the axis of symmetry are actually a part of the solution set to the equation. No, only the points on the parabola are supposed to be like that. So make sure the axis is dotted, but then you draw your parabola. Again, both sides look the same. You've got your arrows on both ends. All right, and that's pretty much it. Make sure the vertex is either the top or the bottom of the parabola. Okay, in this case, it's the top because it goes upside down. All right. The last two things they ask for once again is what's the domain and range. The domain and the range. Okay, we talked about this back in section 2.3. Let me review that with you real quick here. When you take the domain and range by looking at a graph, all right, very similar problem here. It looks like a parabola here as well. All right. Let me just tell you right off the bat, you guys, because a domain and range, let me back up actually, because a parabola goes forever to the left and forever to the right, because it has two diagonal arrows that both go forever to the left and forever to the right respectively, that means that the domain of any parabola, as long as it's one of these parabolas we're looking at here, not a sideways parabola, which we'll probably look at later here at some point, but this normal type that goes either down or it goes up, like this one right here, the domain will always be negative infinity to infinity, always. The range, though, is done by remembering that range is low to high, all right, meaning that you take the lowest point, figure out the y value there, and then you take the highest point. So here, the lowest y value would be 2 because this is the lowest point of the graph, and that's why that was 2, and then it goes upward forever, all right, and so that's why the highest point is infinity. Well, this is the opposite thing right here. It goes downward forever because these arrows tell us that, so the range actually starts at negative infinity. The range always starts at negative infinity if your graph points downward, okay, at any point on the graph. Just like this one did over here. This one points downward, all right. It points downward and to the right at the same time, but downward is one of those two things. All right, so therefore it is definitely going to start at negative infinity. What is the highest point? Well, the highest point actually is right here. It doesn't go upward forever. It's right here, and the y value, which I need to focus on because the range is the y values, not the x values. The y value there is 1. And so the range is negative infinity to 1. All right. So review that in 2.3 if you need to, but that's the domain and range right there. The other thing they want us to do, last thing, is it says find the intervals in which the function is increasing or decreasing. When they say the intervals, they're talking about the x values right here. The x values in which the function is increasing or decreasing. Okay, all you got to do on this, you guys, is realize that as the graph moves from left to right, you got to go from left to right on this. But if I take my pencil as I'm starting up from the left of my graph and going to the right, eventually what's going to happen is it's going to go up all the way until you get to x equal to 2. Again, we're focusing on the x values here. It goes up all the way up until you get to x equal to 2, so that means it's increasing when it's going up. All right. And so because the domain started out at negative infinity, which means the x values started at negative infinity, that means that the increasing part of it began when? It began when we were at negative infinity, okay, because this thing actually goes on forever to the left, even though it's hard to see that without going way down here, but it does. All right, so the domain starts at negative infinity, and so will the beginning of the increasing, all right, and then it'll go all the way up to where? Where does it stop increasing and start going down? At x equal to 2, so we go like this. Put a round bracket right there, all right, because right at 2, you guys, that's not included due to the fact that that's where it turns. All right, so you should never have any square brackets on these increasing, decreasing parts, because the vertex which is where it's going to change from increasing to decreasing always. Okay, that is just where it's turning. So there's neither increasing or decreasing going on there. Where does it start going down? It starts going down at 2 and keeps on going down all the way to in x equal to infinity, because the x's go all the way to infinity here according to my domain. All right, so 2 to infinity. All right, so that's the domain and range. That's the increasing and decreasing. Right. The most important thing is that you can graph it, but they want you to also mention these additional things right here. Okay. All right, now as we look at problem number 2, once again, as we talked about, this is a different type of format here, so we can't do that HK thing here. What we do instead is realize that it looks like this right here. So, in fact, let me put it right above it here so you can see 2x squared minus 4x plus 5. And so what does that mean? That means that the A is equal to 2, right? And the B is equal to negative 4, all right? That's all we need to know right now. The C is not needed yet, okay? But the A, this is the A and the B, all right? And that's going to be really important because the vertex is, the X part of the vertex anyway, is negative B over 2A. Negative B over 2A. Let's go through that carefully. We're going to need to know that in order to be able to figure out what the vertex is. All right, so negative B over 2A. Let's write that down here. Since the B, and let me write it down up here. We already wrote it down at the top of the page, but the A is 2 and the, sorry about that, there it is. The A is equal to 2 and the B is equal to negative 4. And so how does this work here? This negative sign right here changes the sign of whatever this fraction ends up being equal to. We'll get into that, but just to give you a little heads up there. So the B is negative 4 if I plug that in, all right, and then I plug in 2 times, and then the A goes in here. What you do is you figure out what the fraction is equal to first. Okay, we got negative 4 over 4, don't we? Negative 4 over 4 is equal to negative 1 if you actually divide that. All right, if you're able to divide it, otherwise put it in lowest terms. Either way, it's going to end up being negative 1 over 1, same thing as negative 1. So anyway, we got the negative on the outside, which is separate from what the fraction is. The fraction itself is negative 1, and so the negative on the outside, what that means is it means negative 1 times whatever the fraction is equal to. All right, negative 1 times whatever the fraction ends up being equal to, and so that would be negative 1 times negative 1 equal to 1. So now, what is going to be the y part of the vertex? Remember, this is just this negative b over 2a thing. That is just the x part of the vertex. So the vertex overall is going to be what? It's going to be 1, comma. In order to figure out the y portion of the vertex that goes with 1, what we need to do is, since it's supposed to go with 1, it would make sense that we would plug the 1 into this function up here, because again, anytime you plug a number into x and then you figure out what the function value is, it will automatically be the number that pairs up with 1. We found that out in chapter 2. So what would that be here? Let me just write it down up here and give myself some room. F of 1 is equal to 2 times 1 squared minus 4 times 1 plus 5. All right, if I do the normal order of operations here, I won't show the work this time. We've done this kind of thing many times before, so I'll let you do that on your own. But that ends up being equal to 3, all right, equal to 3. And so the vertex, now we have the whole thing, 1 and 3. Once we got that, then just like I told you in the previous problem here, because the x part of the vertex is equal to 1, then you just need to plug in a number on each side of 1, all right? And the same distance away, preferably, so that you only have to calculate it once. Notice that 0 and 2 are the same distance away from 1, right? 0 and 2. So if I plug in 0 and 2, the great thing about that is that once I figure out 0, 2 will be the same y value, all right, as we talked about in problem number 1. Well, if I plug in 0 right here, you guys, isn't it true that when you plug 0 into a polynomial, all of the terms that have variables in it. And this is a trinomial, isn't it? This is a 3-term polynomial, just your normal, no brackets or anything, just a normal polynomial. You plug a 0 into that, the terms with the variable will automatically become zeros, and so you have 0 minus 0 plus 5. 0 minus 0 plus 5 is 5. That always happens with a polynomial, you guys. All right. Basically, the x terms disappear when you plug in 0. This only works for 0. And then so the constant term, if there is one, that is what it ends up being equal to, 5. And so that must mean that 2 gives you the same thing, 5. All right. Now, again, since these numbers are relatively small here, we don't need to change the scaling. 1 comma 3 is going to be right here. 0 comma 5 and 2 comma 5 are right there in those two spots. All right. And so we get what here? Again, make sure your parabola is smooth. All right. And all that good stuff. And put your axis on here like we talked about. Dotted line. Okay. And just make sure it looks the same on both sides of that, but it's smooth here like a U shape. All right. There we go, and that's your parabola. All right. Once again, they wanted to know those last two things right there. They are what's the domain and what's the range, and then also that increasing, decreasing stuff. All right. The domain, like I said, is always going to be negative infinity to infinity when you're doing a parabola. Okay, one of these up or down parabola type problems. The range this time, though, because there's a lowest point, the lowest y value does exist. It's not infinity or negative infinity. This time it's equal to 3. Okay. And then the highest point, because the graph points upward, that means it goes upward forever. And the range always ends at infinity when it goes upward forever, because that means there's no highest point. And it always is supposed to end at the highest point. And so there's your range. All right, now what about the increasing, decreasing? Well, remember in the last problem, the increasing, decreasing always split. See how it split apart at 2 right here? Went from negative infinity to 2 and then 2 to infinity. All right. Well, this time, first of all, the decreasing is the one that happens first because you go down and then up instead of up and then down like you did over here. So the first one is actually going to be the decreasing one this time. But what does it change? Where does it change direction from going down to going up? It changes at x equal to 1. X equal to 1. Remember, we're looking at the x values when we do the increasing, decreasing part. So it's going, it's decreasing all the way up to 1. And so we say decreasing from negative infinity all the way up to 1. Very similar to this, where you go negative infinity to the point where it changes. All right. And then see how we went, it ended at 2 here, and then it started at 2 here. Same thing on this problem. It ends at 1, and then it starts at 1 all the way to infinity for the other part. In this case, the increasing is the other part, because again, you're going decreasing first all the way up to x equal to 1, and then you're increasing from 1 all the way to infinity. This keeps on going out to infinity, even with the x's, all right? And so that's why it comes out like that. So sometimes your problem is going to be increasing on the left and then decreasing on the right, and that's why it ended up like this, okay? But sometimes it's going to be decreasing first and then increasing. And when that happens, the decreasing has to be negative infinity up to something, and then the increasing goes from that turning point all the way to infinity. All right. Number 3 is very similar to number 2. All right, it has that similar format there. Once again, the A and the B are what we're concerned about here, so we can figure out the vertex. The A is negative 3, and the B is 24. So what is going to be the negative b over 2a fraction, which is the x part of the vertex? What is that going to be? Let's plug in these numbers here. We get, and we got a lot of negatives here, so be careful. Oh, Actually, not that many negatives. I didn't mean to say negative 24 there. I meant positive 24. But let's plug in 24 into B and negative 3 into the A, as it tells us to up here. And so we get, first of all, you got to figure out what the fraction is, not including the negative outside of the fraction. We'll get to that at the end. But isn't this 24 over negative 6? And what is 24 over negative 6? That is equal to negative 4. And so then, now that I know what the fraction is equal to, multiplying that by negative 1 on the outside of the fraction, I get positive 4. So that means that the x part of the vertex is 4. The question now is, what is the y part of the vertex? The y part of the vertex, again, is found by plugging in. I'll go ahead and show the work this time, I guess. I'll write kind of small, though, so I can fit it in here. The f of 4, if I plug in the 4 into x, I get this right here. Okay. And so what does that end up being here? Exponents first, then the multiplication. So I get negative 36 plus 96 minus 46. And then we have to add and subtract from left to right. Okay, you got to do it from left to right when you get to the addition and subtraction step. So we get what? We get 60 minus 46 is going to be... oh, I'm sorry. Pardon me. You guys probably noticed that already, huh? 4 squared is not 12, it's 16. There we go. So that's going to be what? That's going to be negative 48 right here. And so now negative 48 plus 96 is going to be 48. 48 minus 46, it's equal to 2. And so that means that since the function value was equal to 2, that must be the y value. Okay, so I'll put that into the vertex. All right. Now, as we've talked about in the last couple problems, when your x value is equal to 2, in fact, we saw that same exact x value in the first problem. If your x value for the vertex, that's the y value. The x value for the vertex is 4. So since it's 4, we can then pick what? We can pick 3 and 5. Again, two numbers that are the same distance away from 4, all right, and it'll give you the same y value guaranteed, okay? Only with parabolas does that happen, okay, but all of these are parabolas in this section. So anyway, if I plug in 3, let's see what happens with that one. F of 3 is negative 3 times 3 squared plus 24 times 3 minus 46. All right. So the exponent is 9. The multiplication gives me negative 27 plus 72 minus 46. And I'll just do the last two steps here, distance subtraction all at once here. I get 45 minus 46 is negative 1. So that means that both of these have got to be negative 1. Sorry, again, that fell off the screen. Let me zoom out there so we can get all of that in here. There we go. So that means that both of these are negative 1 right here because the function value was negative 1. Again, these values are small enough that we can fit these on here without changing the scale. There's the 4, 2 right there. All right. And 3, negative 1 is right here. 5, negative 1 is right there. Put your axis of symmetry on there. And then draw your parabola. Make sure it's smooth. I know it's kind of hard there when the parabola is kind of skinny, but see what I'm doing right there? Just make sure that it looks smooth right there. and then it didn't make a sharp V-shaped type of turn there. All right. Okay, so you can see here that I'm making extra sure that everybody knows that that's a nice smooth turn right there at the top. All right, there we go. So to wrap things up here, what is the domain and range? Okay, the domain is always the same, isn't it? Negative infinity to positive infinity, always the same thing. All right. There we go. That's fine right there. And then the range is what? The range is going to be just like the first problem, because it goes downward forever. That means the range always starts at negative infinity. And because there is a highest point and the y value there for the range is 2, then that means the range ends at 2. Like that. Okay. What about increasing and decreasing? Because it's increasing first and then decreasing second, the increasing is going to start at negative infinity and go all the way to where it turns. It turns at x equal to 4. And then it starts decreasing after that, right? So that means that the decreasing part will start at 4. Not negative 4, excuse me. Starts at 4. And it goes all the way to the end. So that means it goes all the way to x equal to infinity. And there you go. All right, so that's your domain, range, increasing and decreasing. And this concludes our discussion on parabolas. All right, and these two particular formats here. All right, and knowing how to graph those. There is still a backside to the worksheet, but that will be on a separate lecture video. So for now, contact me if you have any questions. Have a good day.